briefly discuss. The first question is essentially to look at this is a biaxial medium, and a circularly polarized plane wave has to propagate unchanged. This will happen provided the two eigenmodes have the same velocities. Circular polarization has nothing to do with the problem. Any polarization state will retain itself, provided the two eigenmodes have the same speed. So all I need to do is to calculate what is the angle with respect to z-axis where the two eigenmodes have the same speed. So I have done in the class the refractive index as seen by one polarization which lies in the z plane and the other polarization which is parallel to the y-axis. So all I need to do is to put the refractive index of the y polarization state as the same as the one which lies in the plane of the paper. So essentially the problem is I have x and z, so it's some propagation direction. So if you propagate the z plane, remember I had done in the class, one polarization is E along y cap and the other one is E in z plane. And the two refractive indices we had calculated, one was ny, the other one was 1 by n square of psi is equal to cos square psi by nx square plus sine square psi by nz square. So I had to put this 1 by n square of psi is equal to 1 by ny square and solve the equation for psi. That will give you the direction of propagation in which the two eigenmodes have the same speed, and so polarization state will not change as the wave propagates. The second part was essentially the second question is breaking up the input polarization state into one which is ordinary and the other is extraordinary. The ordinary one is perpendicular to the plane of the paper, the extraordinary one is parallel to the plane of the paper. And the ordinary one will go undeviated, and so the electric field which is incident like this has one component along the ordinary axis and the other on extraordinary axis. So the ordinary one will propagate unchanged, and so it's a y polarization direction, and the intensity of this is cos square of this angle. So that's 0.75 watts per square meter. Okay, C problem was very simple. It's essentially using this formula for the sinc function. And many people have made a mistake there. Actually, you have to calculate what is the efficiency with delta k is equal to 0. And then calculate the value of delta k for which the efficiency will be not less than 81% of the delta k is equal to 0 value. And some people have actually forgotten about the z square factor in calculation of the efficiency. So there's a problem there. The D part was similar to what we have been doing in the class. Essentially, the polarization state of the omega wave is along the y-axis. The electric field has only y component, and from the D tensor, you can actually calculate the polarization generated in the medium at second harmonic. The E part is essentially to realize that the number of photons that you are generating is half the number of photons that you're losing. That's your. So, unfortunately, some people have used the wavelength of the fundamental in calculating the number of photons, not the wavelength of the second harmonic. Okay, so please remember that you can calculate the power in the second harmonic, which is 2% of the input power, because the efficiency is given as 2%, and that power divided by h cross into 2 omega, because 2 omega is the frequency of the output photon. In second problem, the second question, I had sort of numerically estimated a delta k function as a function of wavelength, and the first part was simple. Actually, what I wanted in the second part, it was not very clear in the question. Actually, the question was, if I made a device with the capital K value which is calculated above. So there was a mistake in the question. There was a sort of a, not a mistake, ambiguity in the question. And so I marked both answers to be right. So what I wanted to calculate is if I assume a device with that capital K obtained in the first part, what is the bandwidth over which I will have significant efficiency of second harmonic generation? If you plot, for example, if you would plot efficiency as a function of wavelength, you would have got like this, something like this. This is 1 micron here, because this is the place where delta K is equal to K. So I wanted actually these numbers here, this value and this value, just to give you an indication of how large is the bandwidth. So please, those of you who have not done this, go back and just do this. From this question, please calculate what is this delta lambda, the bandwidth over which the second harmonic efficiency has its peak. If you deviate in wavelength from this point much, this efficiency will drop down to negligibly small values. So sinc square function, and what we have calculated is a sinc delta function, sinc of sine delta K z by 2 by So if I take a quasi phase matching, I'll have sine delta K minus K into z by 2 by delta K minus K into z by 2 whole square. So you can make delta K is equal to K at one particular wavelength, 1 micron, and then if you change the wavelength, delta K will change according to the formula which I have given. So what will happen is, at some value of delta K, the sine function will become 0, and you will get zeros of efficiency. And this problem was just to give you an indication. In fact, it's an extension of a problem which I had given in the class, which I still want you to do. Analytical expression for this delta lambda, or delta omega. What is the change in the wavelength from the central frequency or wavelength at which the efficiency will drop to 0? I want you to calculate. So it looks like if I give you a homework, you're not doing it. So I would like you to submit it. Please submit this assignment next week. Please calculate what is the delta omega or delta lambda, so that the efficiency drops to 0. So I have at lambda is equal to lambda 0 or omega is equal to omega 0, some frequency, some particular frequency, I have eta is equal to delta K is equal to K. So at lambda is equal to some wavelength plus delta lambda plus minus delta lambda, or omega is equal to omega naught plus minus delta omega, eta becomes 0. So
is it a constant divided by 2 and dash 2 omega minus and dash 2?
Sorry?
A constant divided by 2 and dash 2 omega minus and dash 2.
What is n dash?
This dn by.
It is relative derivatives. So why a constant? There must be some.
There was value, I don't know.
Yeah. There is, yes, exactly. It depends on the difference in the dispersion values of the phase dn by d omega at the fundamental and dn by d omega at the second harmonic. That difference will determine what is the bandwidth of this interaction process, and one can actually check that this bandwidth is usually very, very small, few nanometers, not more than that. So that means your wavelength of the laser has to be very, very precisely defined for a given quasi-phase matching interaction process. If your wavelength deviates by a few nanometers, the efficiency drops to almost 0. Okay, so this is a problem just to give you some indication of what parameters are involved. So if I want to increase the bandwidth of interaction, what I should do? There are people who are interested in having a situation where no matter if the wavelength of the laser deviates slightly by a few nanometers, efficiency should not drop significantly. So what I should do? So if I have an analytical expression, I would know what I need to do to design a device where even if the frequency or wavelength changes slightly, the efficiency does not drop significantly. So that means larger this delta omega is, larger the bandwidth. Sorry?
The variation of the refractive index with omega should be less.
At what frequency? Please check carefully. Should the dn by d omega be less, or should I relate dn by d omega at omega and to omega frequency, or what? Okay, so please check this. Okay, so I will please submit this next week sometime. So this problem actually I did not want to give this in the question because this is a little more trickier. But this so I actually simulated a delta K variation with wavelength for lithium niobate and just put it in the question paper. Okay. So the second part was for this particular problem because actually remember I've written that the region of wavelength for which this is valid is 990 nanometers to 1010 nanometers. If you do assuming delta K is equal to 0, this wavelength comes to 1.3 microns. So this is not valid actually in that expression. This validity of this expression just goes off. But anyway, I have still maintained that. Okay. Well, there was a little bit of ambiguity in this question. Okay, the last question. Please do not forget the n refractive index sitting in the power expression. The power is related to n times mod e square. So the fundamental, if the power in the fundamental, what you need to show is d by dz of P1 plus P2, and P1 is N1 by 2C mu 0 mod E1 square into the area. And similarly, P2 is N2 by 2C mu 0 mod E2 square into the area. So using those two differential equations for E1 and E2, you can actually show d by dz of P1 plus P2. And this irrespective of delta K being 0 or not 0. If delta K was 0, then N1 becomes equal to N2, and it simply becomes d by dz of mod E1 square plus mod E2 square is equal to 0. But otherwise, it is d by dz of N1 mod E1 square plus N2 mod E2 square, which is 0. Because 1 by 2 C mu 0 S is common. So if you substitute those differential equations, you will get this condition. Okay, so please just do it for your own sake. Yeah.
Why can't we say that the energy density d by dz of the energy density, d by dt of the energy density will be the same? If I write that d by dt of the energy density is 0.
No, but for energy, not the energy density. It is the amount of energy crossing a unit area per unit time, or some area per unit time. That depends also on velocity. Because energy density into velocity is the intensity. So the power that is crossing here should be the same, should be conserved. That will depend on energy density, of course, and the velocity, which is different at different frequencies, because the refractive index comes into picture. Okay, so it's just not energy densities, it is the velocity also into picture, which is the intensity, amount of energy crossing per unit time. Yeah, either per unit area or in the total area. Any questions? Okay, those of you who might have to recheck the answer script, just give it back to me, I'll have a look at it. Yeah. Lovely, huh? Yeah.
And then I said for no change in polarization.
Okay. Anything else? Just mark. Just write which question, Pooja. Yeah. Anybody who came late? What is your name? Ashish Kumar. Okay, any questions? Okay, let's continue our discussion on parametric amplification or difference frequency generation. So let me recall. What we have essentially is, inside the medium, I have three frequencies simultaneously, omega p, omega s, and omega I, satisfying the condition omega p is equal to omega s plus omega I. So as I said before, if the input corresponds to omega s and omega I simultaneously present at the input, then this is looking at some frequency generation. If I have input at omega p and omega I, or omega p and omega s, it is looking at amplification. So all these processes are controlled by these three equations which we have derived: I kappa p, es, ei, exponential minus I delta k z, des by dz is equal to I kappa s ep, what will I get? ei star exponential I delta kz, and dei by dz is equal to I kappa I ep es star exponential I delta kz, where delta k is kp minus ks minus ki. And kappas are the coupling coefficients. So kappa I is omega I d by c times ni. I corresponds to either the pump, P, S or I. Actually, I should, some other index may be kappa alpha is equal to alpha. So alpha can be pump, signal or idler. Okay, now last time what we did was, so we started looking at the following problem. We started looking at difference frequency generation. What was the input condition we had assumed? We had assumed the input of pump and signal, P and S were input. Now, before I really look at that problem, let me look at these equations and show you another condition that is being satisfied by these equations. Now, again, I will show this condition for delta k is equal to 0, but please do it for delta k not equal to 0. Okay? So, delta k is equal to 0. Let me calculate the following quantity, dpp by dz. Pp is the pump power. So, this is d by dz of np by 2c mu 0 ep star into the area. Intensity multiplied by area. So, this is np s by 2c mu 0 ep star dep by dz plus ep dep star by dz. So, I can substitute from here, I can substitute the expression for dep by dz from here and dep star by dz. So, I will get np s by 2c mu 0 I kappa p ep star es ei. Please note that the second term is the complex conjugate of the first term. So, I will get minus I kappa p ep es star ei star. The second term is the complex conjugate of the first term, and kappa p has only real quantities, omega alpha, omega p, d, c n p, everything is real. So, I will have np s by 2c mu 0. I can take out kappa p, I times kappa p outside. So, I will have I here. Kappa p is omega p d by c times np into ep star es ei minus ep es star ei star, which is equal to I, so np goes off, s times d by 2 c square mu 0 into omega p into ep star es ei minus ep es star ei star. Okay. Now, I can do the same thing for dps by dz and dpi by dz. So, I leave this to you to please show dps by dz will be I s d by 2c mu 0, 2c square mu 0 into omega s into ep es star ei star minus ep star Es Ei. Verify the right equation. Yeah. And similarly, dpi by dz, please show it's I S d by 2c square mu 0 omega I EP Es star Ei star minus EP Es Ei. Okay, now let me put these three equations together. So I have the third equation here. Let me rewrite this third equation. dp by pp by dz is equal to I S d by 2c square mu 0 omega p, sorry, this is EP star, EP star Es Ei minus EP Es star Ei star. I'll just read it in the last equation for dpp by dz. Now what do these three equations tell me? First thing I notice, so I divide by omega p on this side, omega I bring it here, omega s I bring it here. So what do I get? Please see, these are just the opposite. This is the negative of this is negative of this. So I get 1 minus 1 by omega p dpp by dz is equal to plus 1 by omega s dps by dz is equal to plus 1 by omega I dpi by dz. One by omega p dp by dz minus of that, we'll just interchange these two terms, is equal to plus 1 by omega s dps by dz is equal to plus 1 by omega I dpi. These are called the Manley-Lower relations. So how would I interpret these equations? Yes. Please note that if I divide every term by h cross,
This is rate of change of energy per unit energy of each wave. So sort of you can say that.
not per unit energy, per unit distance, rate of change
Rate
in
of
distance.
change of the energy
Yeah.
per unit the energy of the wave. I mean, we divide it with the initial energy of the wave, and we say that
No, where is the initial energy of the wave?
h cross omega b is the initial energy of the. Okay.
That is energy of a photon. So what is pp by h cross omega p? pp is the power, the amount of energy crossing per unit time. Number of protons crossing per unit time.
Unit distance.
Intensity is per unit area, but there's no intensity. I'm talking about power. So pp by h cross omega p is the number of photons at the pump frequency crossing per unit time, that area. Minus of that, the rate of change of the number of photons at the pump frequency crossing is equal to plus of the rate of change of the signal photons is equal to plus of the rate of change of the idler photons. So what does it mean? It means that every time I lose one pump photon, if dpp by h cross omega p by dz is 1, if this is minus 1, this is plus 1, and this is plus 1. So it means that every time the process, what is happening is a pump photon is splitting into a signal photon and an idler photon. Please note, I have not brought photons at all into the picture till now. This is purely classical argument. This is a purely classical analysis. I'm just using Maxwell's equations. But if I interpret h cross omega p as a quantum, pp by h cross omega p is a number. It gives you the number of photons, I call photon, these photons per unit, which are crossing per unit time across the area. So the rate of decrease of the number of pump photons is equal to the rate of increase of the signal photons is equal to the rate of increase of the idler photons. Now I'll leave it to you to use this equation and to show that d by dz of pp plus ps plus pi, the sum of these three will simply be 0. Because omega p is equal to omega s plus omega I. If I add these three equations, I will get this minus this minus this. These three will be equal. I will get omega p minus omega s minus omega I, which is 0. So I will get the energy conservation condition d by dz of pp. What I'm getting is d by dz of pp plus ps plus pi is equal to 0. So this is a very important relationship, which tells me essentially that this process is as if pump photons at frequency omega p are splitting to give you a single photon at omega s frequency and an idler photon at frequency omega I. And this is the condition satisfied by these three. This is a very important relationship, and this is a quantum mechanical relationship also, because essentially it is showing that although my analysis is classical, it is showing that it is as if the number of photons which I've lost at the pump frequency must be equal to the number of single photons I've generated and the number of idle photons I've generated. So there is no conservation of number. If I pump in 100 pump photons and convert them into signal and idler, I will have 100 single photons and 100 idler photons. So I come in with 100 photons, but I come out with 200 photons, but each photon has a lower energy. There is no problem of energy conservation. Okay? Okay, so now what we did last time was look at this equation. So the problem we started looking at was I have omega p and omega s. And we are looking at the generation of omega I, which is equal to omega p minus omega I. So for this we had to solve these two equations. d s by dz is equal to I kappa s EP EI star, and DEI by dz is equal to I kappa I EP EI star. This is assuming delta k is equal to 0. Let me emphasize again that even if delta k is not equal to 0, if I want to do quasi-phase matching, I will get the same equations, except that in kappas, the d which I am using will get replaced by an effective d value, 2 by pi times d if I am using first order quasi-phase matching, or 2 by 3 pi d if I am using third order quasi-phase matching, etc. Because I will pick up one of the Fourier coefficients of the periodic function, and that will be responsible for the generation. So kappa will just get replaced. So kappa is right now is omega s d by c times ns, and d is the effective nonlinear coefficient. If it is quasi-phase matching and perfect quasi-phase matching, these are again the same equations, except that I need to worry about d. D may not be the actual d coefficient of the crystal, it is the Fourier coefficient in the quasi-phase matching case. Okay? So these equations are for a situation where I have either perfect phase matching or perfect quasi-phase matching with no exponential phase term sitting in these equations. What I had shown you is the solution to these two equations with this condition gave me the following two solutions. Can you recall what were the solutions we got? Ps of z is equal to Ps of 0 into what are the solutions we had obtained last time? Cos hyperbolic square Gz, and Pi of z was omega I by omega s Okay, so what is the increase in the number of signal photons from z is equal to 0 to some value L? So suppose the interaction started at z is equal to 0, it comes to z is equal to L. So here the input was Ps of 0, here I am getting Ps of L, So delta PS, change in the signal power is PS of L minus PS0, which is PS0 into cos hyperbolic square GL minus 1, which is how much? Cos hyperbolic square GL minus 1. Sine hyperbolic square. Yeah.
When we write pi of z,
Yeah.
so pi, that means ni times mod ei square, sort of.
Yes. Yes. Pi 2 C mu 0 into the area of cross area of the beam. Yeah.
So there would not be an ni.
Sorry. Electric field had an ns by ni. Kappa s. Kappa I by kappa s. What was the expression we had obtained last time? Can you go back and look at the equation?
Yes,
Omega I by omega s, PS0 sine hyperbolic square gz. Yes. There is no ns by ni. In the electric fields, we had this ni and ns also sitting, but not in the power. And delta pi is simply pi of L, because pi of 0 is 0, which is equal to omega I by omega s PS0 sine hyperbolic square GL. Now, why is this extra factor of omega I by omega s sitting here?
because they are not equal. Otherwise, they were equal when we had second harmonic, when the parametric down conversion, it was omega and omega, so it was cancelling.
No, here, but mathematically, I have an extra omega I by omega s sitting in the expression for the change of power in the idler. So it looks as if the power in the signal coming out, extra power in the signal is not equal to the power in the idler. Why?
Because frequency that the number of photons are same.
Ah.
Change in number of photons.
The number of photons, extra number of photons coming out at signal is delta PS by h cross omega s. The number of idler photons coming out is delta pi by h cross omega I, and they are equal. So delta PS by h cross omega s is equal to delta pi by h cross omega I, because it is the number of photons at the signal that have been added to the signal by the amplification process must be equal to the number of idler photons that have been generated in the down conversion process. And because the idler frequency is usually smaller than the signal frequency, the power in the idler is smaller. It has the same number of photons as the additional number of photons in the signal, but because its photon energy is smaller, the power in this idler is smaller than the power in the signal, assuming omega s is bigger than omega I always. So this factor is coming simply because of having same number of photons generated at the idler and signal by this process, because every time I have added a photon in the signal, I have added a photon in the idler. And the photon at idler has a lower energy, and hence the power coming out of the idler is smaller than the additional power being generated at the signal frequency. And also notice that there is no dependence on phase. No matter what is the phase of this input signal, no matter what is the phase of this input signal here with respect to pump, PS is always increasing with z. This is always increasing. Cos hyperbolic square gz is an increasing function of z. So this is a situation where it acts like a phase insensitive amplifier. This amplification process is insensitive to the phase of the input signal. Now, let me go to the following situation, which is very interesting, where I say that I have omega p, omega s, and omega I. All three inputs simultaneously. I'll show you that now the signal will either get amplified or attenuated depending on the phase relationship between the idler signal and the pump. So what is happening is, in this case, because there is no third wave incident, the process is such that it always leads to generation of signal and idler photons from the pump photon, irrespective of the phase of the signal. So signal always gets amplified. No matter what signal phase is, this interaction between the signal and pump is such that you convert pump photons to signal and idler photons. So the power is flowing from omega p to omega s and omega I continuously in this process. Here, depending on the phase of these waves, I can either generate omega s and omega I from omega p, or I can generate omega p from omega s and omega I, which is some frequency generation. All three waves are present simultaneously. The phase matching condition for generating omega I from omega p omega s, what is the phase matching condition? Kp is equal to Ks plus Ki. This implies delta K is equal to 0. This is the phase matching condition for either some frequency from omega s and omega I to omega p, or difference frequency from omega p and omega s to omega I, because that will be Ki is equal to Kp minus Ks. This is the same equation, same condition. So the condition for efficient interaction between these three frequencies such that omega s plus omega I is equal to omega p is that I must satisfy this condition. Whether energy flows from omega p to omega s and amplifies omega s, or energy flows from omega s and omega I to omega p and attenuates omega s, is determined by the phase of the signal. Now, so what I need to do is, again we will assume no pump depletion. So EP of Z is equal to some EP0. Let me put a phase here. This is exponential I phi P0. This is assumed to be a constant. ES of Z at Z is equal to 0 is ES0 exponential I phi S0, and EI at Z is equal to 0 is equal to EI0 exponential I phi I0. This is at Z is equal to 0. Remember, ES and EI are the complex electric fields of the signal and idler frequencies. So in the last class when we solved the problem, we assumed EI of Z is equal to 0 is equal to 0. Now, I also assume that there is a finite idler present at the input. And I define the phases of the pump, signal and idler at the input as phi P0, phi S0 and phi S0, and assume that the pump depletion is negligible, the pump is powerful, so I just neglect the changes in the pump electric field completely. So I still need to solve only those two equations corresponding to ES and EI. I need to solve again this pair of equations with the boundary condition that this is satisfied. So now remember, we had derived this equation last time. We differentiate this equation with respect to Z, assume EP is a constant, and use the second equation. So actually, we had started with this equation. So what we did was, I differentiate the second equation, so I get d square EI by dz square is equal to I kappa I EP. Sorry, there is a ES star here. I'm sorry, there's a mistake here. This is ES star. So d ES star by dz is minus I kappa S EP star EI. So this gives me kappa I kappa S mod EP square EI, which I called as G square, is it? G square, okay? So G square is kappa I kappa S mod EP square, which is actually kappa S kappa I EP 0 square. EP is assumed to be constant, and EP is equal to EP0 exponential I phi P0. So mod EP square is simply EP0 square. So the solutions of this equation are EI of Z is equal to A sine hyperbolic GZ plus B cos hyperbolic GZ. And then what did you do? We substituted this EI of Z in this equation, and obtained an expression for ES star of Z. So what was the equation? Now let me substitute here. So I kappa I EP ES star is equal to dEI by dZ. So G times A cos hyperbolic GZ plus B sine hyperbolic GZ. So ES star of Z is minus I G by kappa I EP into A cos hyperbolic GZ plus B sine hyperbolic. One solution for EI. Now I have an expression for G here. So let me use that equation here. So what will I get? I will get ES star of Z minus I square root of kappa S kappa I ES0. So EP0. P0 by kappa I. EP is EP0 exponential I phi P0 into A cos hyperbolic GZ plus B sine hyperbolic GZ, which is actually minus I under root kappa S by kappa I exponential minus I phi P0 A cos hyperbolic GZ plus B in the last class. Actually, I had assumed EP was real, but I have assumed a certain phase of the pump here. Okay. So if you use the original boundary conditions, you will get the same solution. Yes, Prasun.
In the earlier case, there was no initial EI.
Yes.
So, but at the later process, EI was getting generated.
Yeah.
But its phase was such that the pump was getting reduced. So, can we say that this particular device acts as a source of coherent waves?
It is source of coherent wave. The idler which is coming out is a coherent source, it's a coherent wave. The frequency, that wave which I am generating at the idler frequency is a coherent wave. It is at one particular frequency. Actually, there is a finite bandwidth. I'll come to this problem later. But it is generating electromagnetic wave at a particular frequency.
No, apart from this, sir, that the phase difference between the two waves that we get at the output, that also remains constant with time and space.
No, not with constant with space. If you go back and look at the earlier equation, theta was maintained at pi by 2 for the second harmonic 2 omega omega process, for example. It doesn't say that phi 1 and phi 2 are constants. For example, when I started with the condition that I had theta is equal to 0 at the input, theta is pi by 2 at the input, plus pi by 2 or minus pi by 2, it remains plus pi by 2 and minus pi by 2. It doesn't mean that phi 1 and phi 2 are constant.
No, sir, I am saying that
Phase difference may be remaining constant, but I have to solve the equation to find out whether the phase difference between signal and idler remains constant. But please note that these are two different frequencies. In principle, at any value of Z, if you look at, the phase difference will remain constant with time because there is no time variation. We are assuming a situation where the pump is a constant signal, constant pump wave coming in. It will generate a signal and an idler. They will have a certain phase difference at the output, and that phase difference will remain constant with time. There is no change with time. But the frequencies are different, right? If I try to put them on a detector, it will beat at the frequency omega s minus omega I.
Sir, this one more thing, sir. Suppose we use in interference experiments,
Yeah.
we use sources.
Yes.
So can I use such type of source in case of interference experiments?
Yes, but these two frequencies are different.
Yes, sir. Although these two are different, but with respect to phase.
Sure. We will come to more intricate experiment later. When I interfere what is called a 2-photon interference experiment, we will discuss a little later. But these two are, in that sense, coherent. The photons coming out of the signal and idler are actually from the same pump photon, and they have correlations which are very interesting. And as I will show you later on, they have correlations beyond what we can imagine classically. Okay, so but this is a purely classical array equation that I'm solving and getting solutions, and there is a phase generated of the idler and signal. In the first process, where there was no idler present, the phase of the idler gets automatically defined by the process, and the signal and idler keep on increasing in amplitude. In this case, because I have chosen the phase difference between these three waves at the input, it is possible that energy flows from omega p to omega s omega I or the reverse process. Okay? So what I need to do is to now, I have two equations. Here is one equation for ES star. Here is an equation for EI of Z. There are two constants A and B. I have to apply this boundary condition. ES at Z is equal to 0 this, EI at Z is equal to 0 so much. Now I will leave this substituting and calculating the coefficients to you, and let me give you the final equation for EI of Z and ES star of Z. So here are the equations. Please go back and just obtain these equations. That means just obtain the constants. So I have I omega I ns by omega s ni exponential I phi p 0 es 0 star sine hyperbolic gz plus ei 0 cos hyperbolic gz, and es star of z is equal to es 0 star cos hyperbolic gz minus I times square root of omega s ni by omega I ns exponential minus I phi p 0 ei 0 sine hyperbolic gz. Please use the boundary conditions. For example, here you see at z is equal to 0, ei of 0 is equal to ei 0. No, let me be a little careful. One second. Let me write this as es of 0. Please correct this. This is because I have defined an ES 0 and EI 0 differently. Let me just call this. That is the signal electric field, complex conjugate of the signal electric field at z is equal to 0. EI of z is equal to 0. ES star of z is equal to 0. EI of z is equal to 0. So these are complex. They have the phase terms inside. Okay, I think we will stop here now. What we will do in the next class is using these equations, I will show you that, as you can see here, you're getting a sine hyperbolic term and a cos hyperbolic term. If you make sure that you have a sum of cosine hyperbolic and sine hyperbolic, it will lead to an increase in amplitude, because cos hyperbolic gz plus sine hyperbolic gz is exponential gz. So it all depends on the phase here, which is coming from here, the pump, and the idler phase from here. So what I will show you in the next class is, depending on the phase at which the idler and signal and the pump are incident, ES and EI will increase with Z or decrease with Z. So this signal, which is input into the amplifier, will either get amplified or attenuated depending on the phase of the idler. So I can go from amplification to attenuation depending on the phase which I choose of the idler frequency, and I'll show you some experimental plots which people have obtained showing very interesting behavior of this amplifier. Also note that in the phase insensitive case, the amplitude was increasing as cos hyperbolic square gz. If I make sure that this leads to a sum of the cosine and sine hyperbolic, it will go as exponential 2 gz, the power, which is faster. Cos hyperbolic square or exponential 2x. Cos hyperbolic square x and exponential 2x. Exponential is faster, much faster. So actually, in the phase sensitive amplifier, you can actually amplify for the same length of the process for the amplifier. You can achieve much more amplification than in the phase insensitive case. But I need to maintain the phase relationship as a constant phase relationship between these waves. If the phase fluctuates, the signal will fluctuate from sometimes it gets amplified, sometimes it gets attenuated. Okay, so that's an interesting problem. And in fact, in the next class, what I will show you is if I come with a signal with an arbitrary phase, I can break that signal into one component which gets amplified, the other component which gets de-amplified. You see, you can break any signal. You have sin omega t plus phi. It is sin omega t cos phi plus cos omega t sin phi. So I can write as one sin omega t term and one cos omega t term. These are called quadrature components. One is varying as a sine, the other is varying as a cosine. So I can actually break up any signal into two components, one at a certain phase and the other one pi by 2 out of phase with respect to this signal. And what will happen is, if this one is getting amplified, this one will get attenuated because there is a pi by 2 phase difference. So I'll show this explicitly in the next class for the omega to omega process. That means when you make omega s and omega I equal here, I get back into the degenerate parametric amplifier process where omega p was 2 omega and omega s is equal to omega I. Okay, so this three-wave interaction is more general. The second harmonic generation and omega to 2 omega and 2 omega to omega is a special case of this three-wave process where the idler and signal photons have the same frequency. Okay, any questions? Yeah.
Initially, we need two different frequencies.
Yes.
But we want to control the phase difference between the two.
Yes.
So how is this generated in actually? How is this done?
I can actually see at the lower frequencies like microwaves and radio waves, it's not very difficult to control phases of signals. But the problem will arise at optical frequencies. So what is now done is you generate these waves from the same original source wave and make sure that there is a constant phase relationship between these waves. If you do that, then you can achieve this kind of things. Otherwise, you need to have a mechanism by which you can keep controlling the phase. If the phase fluctuation is very slow, you can have a feedback mechanism to control the phase. Otherwise, it becomes difficult.
How is it controlled? If you're using a laser, then how am I able to control the phase there? Like this?
No, omega p is a strong wave which is coming from a laser pump source. Then I have a signal and an idler frequency, which are phase matched with the pump frequency. The experiments which I will tell you are actually generating all the waves from the same original source. So they're all actually having a constant phase relationship. And then they show that there is a phase sensitive nature of the amplification process. But later on, when we come into a little bit of quantum mechanics, I will show you some interesting features of this process because of the process in which omega to omega interaction is taking place. There, this phase sensitive nature or two signals, one in a particular phase and one at a quadrature phase difference, get amplified and de-amplified, comes in very handy in sort of modifying the noise at vacuum level. This will become clearer when we come to a little later, okay? Anything else? Okay, thank you.